All right, let's talk about what we mean by the term significance. So what does the term significant mean? Well, the scientific meaning of the word in statistics is a finding that is reliable and unlikely due to sampling error, or what we might call chance. And typically when we have a statistically significant finding, we have rejected the null hypothesis. Now, the probability of the result occurring due to sampling error is expressed in terms of a p-value. So the p-value is the probability that a statistical test result was due to chance or sampling error, and in order to reject the null hypothesis, the p-value will be very small and smaller than the alpha level. So if alpha level was set to 0.05, the p-value will be less than that. Now, the popular meaning of the word for significance is meaningfulness, right? And so confusion sometimes can arise when people, especially laypersons, don't understand the difference between the scientific meaning of the word and statistical meaning of the word, and then the more popular meaning involving meaningfulness. Okay, so let's talk a little bit more about statistical significance. Again, a statistically significant finding is one that is unlikely due to sampling error or chance factors, and they're associated with small p-values. So the p-value has to be less than the predefined alpha level that was set prior to running the analysis. Now, what do you look for in the statistical output? Well, here's some output from JASP, and it's for a one-sample t-test. And the variable that we were looking at here was called temp, okay? And it's not important what that measures right now. But let's just go through the output and you can see what is actually reported. The column that says T is the actual test statistic. Okay, and in this case, T had a value of 6.60. Okay, so this is the T statistic, the actual result from the t-test that was run. DF refers to degrees of freedom. And for a one sample t-test, that's simply n minus 1. It's the number of observations that are truly independent of one another. Then comes the p-value. So the p-value is the probability that the test result, t, okay, is due to sampling error or chance. And you'll notice that in this case, that p-value is really small. It's less than 0.05. So we would reject the null hypothesis, okay? And then the last column is Cohen's d, and this is a measure of effect size. I won't go into how that's calculated right now, but it is a measure of the magnitude of the overall effect of the independent variable on changes in scores in the dependent variable. Okay, so factors that affect statistical significance. Again, statistical significance, when we say a finding is statistically significant, all that is a probability statement about the reliability of a result. So in a one sample t-test, the question we're asking is, what is the probability that the sample mean would show a given amount of difference from the population mean as the result of chance or sampling error? The answer to that is the p-value. So if the p-value is really small, we say, hey, it's pretty unlikely that the result that we observed was due to chance or sampling error. So what does the p-value not tell us? Well, it doesn't tell us the size or the magnitude of the effect. It doesn't tell us its importance or the meaningfulness of the effect. And typically speaking, as sample size increases, because that has an effect on the calculation of the standard error of the mean, relatively trivial mean differences can still result in rejecting the null hypothesis. So we'd be pretty loath to actually conclude that a statistically significant finding is in fact truly meaningful. It could be, with a very large sample, a very trivial difference. Right, and so the standard error of the mean becomes smaller and smaller as the n gets larger and larger, making it easier to reject the null hypothesis. Okay, so we've talked a little bit about statistical significance. Most people, when they hear the term significance, they think in terms of real-world significance, or they might even think in terms of what's called clinical significance. Now, real-world significance kind of refers to this idea of how generalizable are the results from what we found in a study back to the real world. And there typically is a trade-off, because the more control we exert over how a study is run, the more experimental control, typically speaking, the more artificial the study is, the less it sort of replicates the real world, and the less generalizable the results might be to the real world. So there's this sort of tug of war going on between increasing internal validity, which is really designed to help us find an experimental effect to begin with, and its effect on external validity, or how much those results can generalize back to the real world. Related to this is clinical significance, and clinical significance is often discussed in terms of treatment studies. And the question here is that although there might be a reliable difference in the means between, say, for example, a treatment group and a control group, is that difference really clinically meaningful, right? Because if we're going to make recommendations for changing the way individuals are treated, whether it's in a medical sense or in a social sense, or so forth, a lot of those changes require significant resources. And is there a big enough outcome difference with a new treatment to justify or warrant all those changes? So you can have, again, with large enough sample sizes, trivial differences between a treatment group and a control group. What we're really looking for are clinically significant differences, a magnitude of effect, right, that warrants maybe changes in future treatment protocols. So that leads us to a discussion very quickly on the difference between statistical significance and effect sizes. Now, the p-value is our primary statement of statistical significance. It's a statement of the likelihood that a result was due to sampling error or chance factors. And really all the p-value communicates to us is the reliability of the finding, okay? Now, what we're really kind of interested in as well, though, is what's called the effect size. And the effect size is the magnitude of the finding. And it's typically expressed in terms of statistics like Cohen's d, eta squared, partial eta squared, r squared when we do regression. Those would be sort of measures of effect sizes. And really a measure of effect size is a statement as to the overall effect of manipulating an independent variable. So the question that's being answered is really how much variation in scores on the dependent variable is due to manipulation of the independent variable. And oftentimes that is expressed in terms of mean differences in standard deviation units, which is the case with Cohen's d, or as a proportion of the overall variation in scores on the dependent variable that could be accounted for by the independent variable. And that's eta squared, partial eta squared, and so forth, but that'll be coming in future videos. Okay, so big picture. Big picture here. P-values represent the probability that the result of a statistical test, the results of a statistical test, are due to sampling error or chance factors. And therefore, it's a statement of reliability. Lower p-values will increase the likelihood that we're actually going to reject the null hypothesis. And we could say basically that the finding is statistically significant. It's preferable to say statistically significant, just significant, simply because the qualifier statistically, right, really sort of tells the reader exactly what we mean by significant. So the term statistically significant is preferred to significant. A p-value is a statement then, as I said, as to the reliability of a finding. In contrast, effect size reflects the degree to which scores on a dependent variable change because of the manipulation of the independent variable. And there are different kinds of effect sizes that we study in statistics that are calculated a little bit differently. They're either calculations put in terms of standard deviation units or in terms of proportion of variance accounted for and so forth. But they all share in common this idea of, well, what was the effect of the independent variable on the dependent variable in terms of accounting for some degree of change? So typically speaking, as p-values decrease and they get smaller, and we conclude that the likelihood of obtaining the test result becomes less and less likely due to sampling error, correspondingly, effect sizes tend to increase. And this tells us then that statistically significant findings, although reliable, may not necessarily be especially meaningful, especially when we deal with really large sample sizes where we could have very small p-values that are statistically significant, therefore leading to rejection of the null hypothesis. But we could also have very small effect sizes, right? Meaning, hey, it didn't take much of an effect to actually reject the null hypothesis. That would be closer to what we mean by sort of a trivial finding. Okay, in our next video, we're going to be talking about directional and non-directional tests of statistical significance.